All right, so these are the projectile motion homework solutions. I'd strongly advise you to look over these, rework them, not just look at them, but rework them if you have problems uh, for our test, which is going to be a little bit, well, it's going to be next week, which is going to be the week of January 21st, 22nd. At any rate, the first several of these deal with horizontal launch problems. A couple things. One is you want to always draw a picture so you can get the correct scenario in mind. So this one I think was skipping a stone into water, seeing how far it lands away from where you throw it. So I wrote down that the horizontal speed was 26 meters per second and the vertical height was 0.45 meters. So one of the key aspects of most projectile problems is to determine how much time it takes, or how much time the projectile's airborne. So I'm using a vertical equation here. I have no initial vertical velocity, so I can use a simplified version of this position and acceleration formula. 0.45 equals 1 half at squared. Again, you can use 10 as long as you want. Sometimes 9.8 is preferred in some simulations and things like that. So the falling time is 0.303 seconds. So to figure out how far it goes horizontally, I can rearrange our only horizontal formula for projectiles and figure out for every 1 second, this is traveling horizontally at 26 meters, and then it's doing so for 0.303 seconds, so that's a distance of around 7.9 meters. Here's the situation of something, I think someone's diving off. Oh, it's Alex Watros, good job. And notice the correction, he's 16 years old. So he's off a diving board, going off at 4.6 meters per second into the water. We're trying to find this distance as well as the time to fall, so very similar to the first problem. So I know the height, do this formula again, get the time it takes to fall down, plug that time into the horizontal formula and get that he lands 3.8 meters away from where he goes off the diving board. Now, in this particular case for part C, this is a little different. It's asking the speed at which he hits the water. Well, his horizontal speed is always 4.6 meters per second, but his vertical speed changes. You should know that it changes at a very consistent rate of 9.8 meters per second every second. So if it takes him 0.83 seconds to hit the water, then I multiply those two together. That's another vertical formula we've got. And find out that he's moving vertically at 8.1 meters per second. Because there's an independence of vertical and horizontal motion with projectiles, I can simply use the Pythagorean theorem and figure out his overall speed as he hits the water. I could also figure out the overall angle by drawing a triangle with this and using trig. At any rate, it's 9.3 meters per second. For my problem that I came up with, we've got a drone, it's dropping supplies. You want to drop them directly on top of some stranded campers. So question A is, how fast is the package moving after it's released horizontally? 15 meters per second. I think that's the initial speed. And vertically, the initial velocity is 0 meters per second just after it's dropped. But question C, the vertical velocity changes at 9.8 meters per second every second. So to find out how long it's going to take to hit the ground, we use this formula that we've used before. Since this is horizontally launched, we can figure out how far away the package needs to be released. So the key thing is here, if you've got your people over here wanting the package, you don't release it when the drone is directly above them. Otherwise you're going to overshoot the people. And so what you're going to need to do is to release it before them, and that's 52.5 meters away. So again, assuming there's no air resistance, then the drone will be directly above the package when it hits the ground. For problem 27, we've got something going off horizontally at 208 centimeters per second. You can convert that to meters or not. You could find how long it's going to take to go this horizontal distance. So here we're using a horizontal formula to figure out the time because we know horizontal speed and horizontal distance. And then we could work backwards with that known time to figure out the height. So this is kind of working backwards from some of the previous problems. The last two problems deal with angle launch projectiles. I've used a lot of color for those. So just like the one I went over in class on January 14th, The first thing I do is draw a picture, and then I split things up into the vertical and horizontal components. So vertically, this is moving upward, and it's moving to the right. The speed's upward of 4 meters per second, over to the right at about 7 meters per second. To figure out how much time it's going to take to reach the peak, I use a vertical formula. So change in vertical velocity over time. The total time of this, since there's symmetry in the problem and it lands at the same height as it's launched, is double that time to reach the peak, so that's about 0.82 seconds. And then to find out how far something moves horizontally would be multiplying the total time by the horizontal speed. That's around 5.7 meters. To find the peak height, there's a number of ways to do this. I've given you some details here with it. The key is you want to use half the time, or the time only to reach up to the peak or to come down from the peak. And that's because it's reaching its maximum height halfway through the trip. So I tend to think of the second half of the trip where I don't have an initial vertical velocity that gives me a simpler mathematical model. The last problem with problem 29, I've got a horizontal speed and a vertical speed. Again, I separated those out initially because I knew I was going to need to use them for different things. So for part A, figuring out the time to the peak again, using the formula change in vertical velocity over acceleration. I can figure out the total time if I want. I think in this case it only asks for the time up to the peak. If I want to find the total time, I just double that. And then I would get something here where I get the total range this particular way. So I'm going to leave you with that, and we'll go from there. So there's multiple ways to determine this. A lot of different formulas could work. You just want to make sure you don't shove a particular variable in incorrectly, like a horizontal variable, into a vertical condition. Yep. How you doing?
That's cool.
Yeah.
Podcasting?
No, it's screencasting. Just using QuickTime. Well, whatever. Yeah, the smart pens just do not really work anymore. So I used them for a long time. Yep. How you doing?
Okay. I just had a couple, if you have a few moments. If not, I can talk to you later sometime. I wanted to talk to you about when we set up those computers.
Okay.
You remember some things?
You can ask. Yep, give me a sec here, and let me
Yeah, do it. I don't want to.
chapter or